Okay, so we're still on the working with Kubernetes object section, and now we will take a look in the labels and selectors. Let's take a look on it. Okay, so labels and selectors. Labels are key-value pairs that are attached to objects such as pods. Labels are intended to be used to specify identifying attributes of objects that are meaningful and relevant to users, but do not directly imply semantics to the core system. Labels can be used to organize and to select subsets of objects. Labels can be attached to objects at creation time and subsequently add or modified at any time. Each object can have a set of key value labels defined. Each key must be unique for a given object. So we can see here an example of labeling. It has been set inside metadata, and also labels allows for efficient queries and watches and are ideal for use in UIs and CLIs. Non-identifying information should be recorded using annotations. You can see here. So now let's take a look in motivation. And labels enable users to map their own organizational structures onto system objects in a loosely coupled fashion, without requiring clients to store those mappings. Service deployments and batch processing pipelines are often multi-dimensional entities. For example, multi-partitions or deployments, multiple release tracks, multiple tires, multiple microservices per tire, and management often requires cross-queuing operations, which breaks encapsulation of strictly hierarchical representations. Especially rigid hierarchies determined by the infrastructure rather than by users. So let's see a bunch of example labels. We can have release stable, release canary, environment dev, environment QA, environment production. We can also have tire front end, can be tire back end, or tire cache. We can have a partition label and having customer A, customer B. We can have a track label having daily, weekly, monthly, and so on. These are examples of common use labels. You are free to develop your own conventions, so keep in mind that label K must be unique for a given object. So now let's take a look at syntax and character set. Labels are key value pairs. Veiled labels keys have two segments, an operational prefix and name, separated by a slash. The name segment is required and must be 63 characters or less, beginning and ending with an alphanumeric character, with dashes, underscores, and dots, and alphanumerics between. The prefix is optional. If specified, the prefix must be a DNS subdomain, a series of DNS labels separated by dots, not longer than 253 characters in total, followed by a slash. If the prefix is omitted, the label key is presumed to be private to the user. Automated system components such as Kube Scheduler, Kube Controller Manager, Kube API Server, kubectl, or other third-party automation which add labels to end-user objects must specify a prefix. The Kubernetes.io/ and K8s.io/ prefixes are reserved for Kubernetes core components. So let's take a look. Let's remember, veiled label values must be 63 characters or less, can be empty, and unless empty, it must begin and end with an alphanumeric character. It could contain dashes, underscores, dots, and alphanumerics between. For example, here is the configuration file for a pod that has two labels: the environment set to production value and the app label set to nginx. You can take a look here, the labels, and the environment set to production and app set to nginx. So, label selectors. Unlike names and UIDs, labels do not provide uniqueness. In general, we expect many objects to carry the same labels. Via a label selector, the client or user can identify a set of objects. The label selector is the core grouping primitive in Kubernetes. The API currently supports two types of selectors: equality-based and set-based. A label selector can be made of multiple requirements, which are comma-separated, and in case of multiple requirements, all must be satisfied, so the comma separator acts as a logical AND operator. The semantics of empty or non-specified selectors are dependent on the context, and API types that use selectors should document the validity and meaning of them. Note: for some API types, such as replica sets, the label selectors of two instances must not overlap within a namespace, or the controller can see that as a conflicting instructions and fail to determine how many replicas should be present. Caution: for both equality-based and set-based conditions, there is no logical OR operator. Ensure your filter statements are structured accordingly. So let's take a look now in the equality-based requirement. Equality or inequality-based requirements allow filtering by label keys and values. Matching objects must satisfy all of the specified label constraints, though they may have additional labels as well. Three kinds of operators are admitted. You can see the three kinds here, and the first two represent equality and are synonymous, while the later represents inequality. For example, environment equals production here, and tired not equals front end here. So the former selects all resources with key equal to environment and value equal to production. The later select all resources with key equal to tire and value distinct from front end, and all resources with no labels with the tire key. One could filter for resources in production, excluding front end, using the comma operator. So you can do environment equals production, tire not equals front end. On user scenario for equality-based label requirements is for pods to specify node selection criteria. For example, the sample pods below select nodes with the label accelerator equals NVIDIA, Tesla, P100. Here is an example. In the end of my spec, I put the node selector and then accelerator set to NVIDIA Tesla P100. So now let's take a look in the set-based requirement. Set-based labels requirements allow filtering keys according to a set of values. Three kinds of operators are supported: in, not in, and exists, only in the key identifier. For example, environment is in production, key A, tire not in front end or back end, partition or not partition. The first example selects all resources with the key equal to environment and the value equal to production or key A. The second example selects all resources with equal to tire and values other than front end and back end, and all resources with no labels with the tire key. The third example selects all resources including a label with key partition, no values are checked. The fourth example selects all resources without a label with key partition, no values are checked. Similarly, the comma separator acts as an AND operator, so filtering resources with a partition key, no matter the value, and with an environment different than key A can be archived using partition environment not in key A. The set-based label is a general form of equality since environment equals production is equivalent to environment in production. Similar for not equal and not in. Set-based requirements can be mixed with equality-based requirements. For example, partition in customer A, customer B, environment not in key A. So API, list and watch filtering. List and watch operations may specify label selectors to filter the sets of objects returned using a query parameter. Both requirements are permitted, presented here as the would appear in a URL query string, and there are equality-based requirements. You can see an example here. There are set-based requirements, and this example here. And both label selector styles can be used to list or watch resources via a REST client. For example, targeting API server with kubectl and using equality-based, one may write kubectl get pods -l environment production tire equals front end, and this first example here, or using set-based requirements. And the second example here, you can type kubectl get pods -l environment in production tire in front end. So as already mentioned, set-based requirements are more expressive. For instance, they can implement the OR operator on values. For example, kubectl get pods -l environment and production key A, or restricting negative matching via exist operators. Here, kubectl get pods -l environment not in front end. Set references in API objects. Some Kubernetes objects, such as services and replication controllers, also use label selector to specify sets of other resources, such as pods. Service and replication controller. The set of pods that a service targets is defined with a label selector. Similarly, the population of pods that a replication controller should manage is also defined with a label selector. Label selector for both objects are defined in JSON or YAML files using maps, and only equality-based requirement selectors are supported. You can see an example here, or you can do in that way using YAML. Okay, this selector, respectively in JSON or YAML format, as I just said, is equivalent to component equals Redis or component in Redis. So let's see resources that support set-based requirements. Newer resources such as job, deployment, replica set, and daemon set support set-based requirements as well. You can see an example here where match labels is a map of key value pairs. A single key value in the match labels map is equivalent to an element of match expressions whose key field is a key. The operator is n, and the values array contains only value. Match expressions is a list of pod selector requirements. Veiled operators include n, not in, exist, does not exist. The value set must be non-empty in the case of in and not in. All of the requirements from both match labels and match expressions are ended together, so they must all be satisfied in order to match. So selecting sets of nodes. One use case for selecting over labels is to constrain the set of nodes onto which a pod can schedule. See the documentation on node selection for more information. That's it for today. Thank you.